Hello everyone, my name is Shin and I'm a PhD student at UW Medicine. In this presentation, I'm going to talk about overlapping Schwarz, a new decomposition paradigm for large-scale optimization. Here I have four different classes of large-scale optimization problems: dynamic, stochastic, PDE, and network optimization. And these figures represent the algebraic structure of these problems. For example, dynamic optimization problems such as MPC or state estimation problems can be represented by a chain of temporal dependencies. Here, the node represents the time stages and the dynamic coupling produces the edges. Similarly, the algebraic structure of the stochastic optimization problems can be represented by a scenario tree, and the PDE-based optimization problems can be represented by underlying discretization mesh, and the network optimization problems such as optimal power flow and gas network operations problems can be represented by the structure of their underlying physical network. And now we are going to think about what is the general abstraction of these four classes of optimization problems. A key characteristic in common that we can see from this slide is that they all have graph representation for their algebraic structure. So we can derive a unifying abstraction based on the notion of graph. And this gives rise to what we call graph structured optimization problem. In graph structured optimization, as the name indicates, we assume that there exists an underlying graph, which we denote by G, that encodes the overall algebraic structure of the problem. Graph is nothing complicated, but it's just a pair of a set of nodes and a set of edges, which are denoted by V and E respectively. In the simplest case, it can represent a linear connection of multiple nodes. And it can also represent various complex structures, such as the one you saw in the previous slide. For each node in the graph, we are going to assume that it contains the local component of the optimization problem, specifically the local decision variable, local objective function terms, and the local constraints. And the overall problem is constructed by including all the variables for each node and all the objective functions and all the constraints for the entire node set. But this problem is not separable for each node because we allow the coupling across different nodes. In particular, we allow objective function and the constraint functions to be dependent on the variables that are in the local neighborhood. And the local neighborhood is defined as the directly connected nodes. In this way, we are allowing the coupling across different nodes, but that coupling is only allowed within the direct neighborhood. For the rest of the talk, we're going to assume that all the variables are continuous variables as opposed to discrete variables, and all the functions are sufficiently smooth, but they can be non-convex. So this abstraction is highly flexible in the sense that it can represent any type of dynamic, stochastic, PDE, and network optimization problems, and it can also be used to even more complicated formulations such as space-time optimization problems. But what happens if we have multiple sources of complexity in one optimization problem is that the problem dimension can be extremely large, and solving such problem can pose significant computational challenge. And such computational challenge can be addressed by using decomposition methods. In decomposition methods, the original large-scale graph structured problem is decomposed into multiple smaller problems, and the subproblems are solved in parallel and iteratively with the exchange of information at the boundaries. With this method, we don't need to directly solve the intractably large full problem. So in general, we can handle a much larger problem by using decomposition methods. Specifically, in the successful cases, this type of decomposition method can solve the problem with more than millions of variables and constraints in a reasonably short time. Examples of such decomposition methods include Lagrangian decomposition, ADMM, block-Jacobi, or block-Gauss-Seidel. But oftentimes, this type of decomposition methods face convergence issues or exhibits a very slow convergence. And due to this, their practical computational performance may not be satisfactory. And here we propose to address this issue with a novel decomposition method that we call overlapping Schwarz. This method uses the overlaps between the decomposed subdomains to robustify and accelerate the convergence of the algorithm. The idea of overlapping Schwarz is actually not a new idea, but it is originally developed for the solution of large-scale linear system, which typically arises in PDE. And overlapping Schwarz was proven to be extremely effective for such problems. So this method is implemented in state-of-the-art numerical tools such as PETSI. And interestingly, we have found that this method can be naturally be generalized for solving continuous optimization problems such as LPs, QPs, and NLPs. For many large-scale instances, we have demonstrated that this method can actually be very effective. So in the rest of the talk, I'll be explaining what overlapping Schwarz decomposition method is and why having overlap is robustifying and accelerating the convergence of the algorithm. So in order to explain how overlapping Schwarz decomposition works, I'm going to briefly first explain about non-overlapping decomposition. To walk you through this algorithm, I'm going to use this 4-variable graph structured optimization problem with the linear graph. To solve this problem in a decomposed manner, we first partition the original graph domain into multiple subdomains. For this example, we set node 1 and 2 to be the red subdomain and 3 and 4 to be the blue subdomain. Based on these constructed subdomains, we are going to define an iterative procedure. In each iteration step L, and for each subdomain, we formulate the subproblem by allowing the variables in the associated subdomain to vary while fixing the rest of the variable. And by solving this problem, we can update the next guess of the solution. And we repeat this procedure until we converge to the solution. And this is how non-overlapping decomposition works. And in overlapping Schwarz method, we slightly modify this algorithm. And that modification can be summarized by these two keywords, expand and restrict. The first thing we're going to do is to expand. In this procedure, we expand the original non-overlapping subdomain by a user-defined distance omega. By doing this, we can construct a set of overlapping subdomains. And we're going to call this omega the size of overlap. And then a similar iterative procedure can be derived. For each iteration and for each subdomain, we formulate the subproblem by allowing the variables that are in the expanded subdomain to vary while fixing the rest of the variables. And by solving this, we can make an update for the next guess of the solution. But one issue arises here. Since the subdomains now overlap with each other, we have duplicity in the solution on these overlapped regions. In particular, here you can see that x2 and x3 can either come from the red subdomain or the blue subdomain. In order to remove this duplicity, now we apply the second keyword, restriction. Specifically, we apply a restriction operator R to each subproblem solution. This operator discards the part of the solution which is acquired by the expansion, in this case node 3, and only retains the part of the solution associated with the original non-overlapping subdomain, in this case 1 and 2. In this way, we can resolve the solution duplicity issue, and we can make the next guess of the solution without any conflict. And as before, we repeat this procedure until we converge to the solution. And now I'm going to illustrate why overlap is allowing fast and robust convergence. Here we consider 20-node dynamic optimization problem. For this example, we're gonna apply overlapping Schwarz, and for the other example, we're gonna use the non-overlapping decomposition. And now let's see what happens in the first iteration. Here we plotted the solution X against the node index I, and the optimal solution is represented as the black dashed line, and the subproblem solutions are represented as the colored lines. So in the first iteration, both overlapping and non-overlapping decomposition needs to start the iteration with some arbitrary starting point. And due to this arbitrariness, there are some significant errors in the subproblem solution, as you can see from the plots. However, one interesting observation is that as you go into the interior of the subdomains, you can see that the solution quality actually gets improved. Specifically, the difference from the optimal solution and the subproblem solution becomes smaller and smaller as you get into the interior part of the solution. And this observation is not a coincidence, but it is actually coming from a fundamental property of the graph structured optimization problem that we call exponential decay of sensitivity. Based on this recent result, this property holds for any type of graph structured optimization problem that satisfies certain regularity conditions. And this property is being observed in this particular example. And the magic of the overlapping Schwarz is happening during the restriction. In particular, during the restriction, the low quality boundary part are actually discarded, and only the high quality interior part is taken to the next iteration. On the other hand, in the non-overlapping decomposition, due to the absence of this overlap, the low quality boundary part still remains in the solution, and this will adversely impact the quality of the next iteration step. In the next iteration for overlapping decomposition, thanks to the availability of the high quality solution gas, the solution can quickly close the gap from the optimal solution. But non-overlapping decomposition cannot make much progress due to the absence of such high quality solution gas. And if we repeat this procedure once more, overlapping Schwarz can almost converge to a perfect solution, but non-overlapping method is still stuck in the low quality solution. So this example clearly illustrates why overlap enables fast convergence. So far, we have discussed the algorithm with simple examples, but actually this method can be generalized to any type of graph structured optimization problems, such as space-time problems and the network problems. And this is the overlapping Schwarz algorithm for solving a general graph structured optimization problems. I won't go into the detail because the notation is a bit complicated, but from high level, we can see that the key essence of the algorithm actually remains the same in this algorithm. For each subdomain K and for each iteration, we formulate the subproblem on the expanded subdomain while fixing the rest of the variables. And we solve the subproblem and then restrict the solution to remove the solution duplicity, and then we can make an update for the next guess. And we can repeat this procedure until we converge to the solution. So with this, we can apply overlapping Schwarz to any type of graph structured optimization problem, which is in particular formulated as LPs, QPs, or NLPs. And I'd like to highlight that this algorithm is actually not the only way to implement overlapping Schwarz. For example, we can operate on primal dual space instead of purely on primal space as in this case. Also, we can consider implementing overlapping Schwarz in the linear algebra space within the interior point method. So there are lots of flexibility in implementing overlapping Schwarz. So overlapping Schwarz should be considered as a new decomposition paradigm rather than just one optimization algorithm. And by formalizing our previous observation, we can establish the convergence of the overlapping Schwarz method. Specifically, under some regularity condition, in particular, a strong second order condition and the linear independence constraint qualifications, one can show that overlapping Schwarz scheme locally converges with the linear convergence factor alpha, and this convergence rate has the exponentially decaying relationship with the size of overlap of omega. And this indicates that the algorithm has guaranteed convergence if the size of overlap is sufficiently large, and if we further increase the size of overlap, the convergence rate improves exponentially. In other words, we can accelerate and robustify the convergence of the algorithm by using overlap. Still, a trade-off exists here, because as we increase omega, we will keep expanding the size of the subproblems. In other words, we need to deal with a more complicated set of subproblems. So in practice, one needs to tune omega to balance the effect of the improved convergence rate and increasing subproblem complexity. And this constant rho is actually dependent on the conditioning of the problem. And one observation we can make is that this rho becomes too close to zero if we have good conditioning in the problem. So this means that the overlapping Schwarz method is going to be more effective if the problem has good conditioning. And this result applies to any type of graph structured optimization problems. Now, let's see some of the numerical demonstration of overlapping Schwarz algorithm. First, we use overlapping Schwarz as a spatial decomposition method to solve power system state estimation problem for a large-scale power network. In particular, we solved DC power system state estimation problem for about 9,000 bus system. In the first figure, we plotted the convergence profile while varying the size of overlap. Here, we could clearly see that by increasing the size of overlap, we have faster convergence to the solution. We also compared overlapping Schwarz with the popular decomposition method ADMM, and we could see that overlapping Schwarz finds the solution faster than ADMM, almost by a factor of 10. And here's another case study where we used overlapping Schwarz as a temporal decomposition method for solving a nonlinear MPC problem for a chemical reactor. For this example, we could see that also see that increasing the size of overlap accelerates the convergence of overlapping Schwarz. So this reinforces our previous observation. And furthermore, we could see that for sufficiently long horizon instance, which is formulated as NLP with 10 to the 5 dimensional, 10 to the 5 variables, by sufficiently increasing the number of cores for overlapping Schwarz, we can actually make overlapping Schwarz faster than the centralized over IP opt. And lastly, we used overlapping Schwarz as a linear solver for within the interior point solver. We applied this to solve large-scale challenging space-time optimization problems that arise in energy infrastructure systems. In particular, we considered two problem classes, transient gas network problem and the multi-period AC optimal power flow problem, both of which are formulated as NLPs. And in order to use overlapping Schwarz within the interior point method, we implemented a new nonlinear optimization solver made NLP.jl. And with this solver, we could compare the performance of NLP configured with overlapping Schwarz against the NLP configured with the conventional centralized solver MA57. And from this result, we could see that for the large-scale instances, overlapping Schwarz is much faster than the centralized configuration. In particular, For the problem with about 10 to the 6 variables, overlapping Schwarz was faster than the centralized configuration by almost a factor of 3. So to summarize, these numerical studies demonstrate that with overlapping Schwarz, we can solve various challenging optimization problems that have been difficult to solve with the centralized or conventional decomposition algorithms. And this brings us to the end of this presentation. And thank you very much for attending this talk.